you guys do the bell ringer?
Oh, bell ringer, I heard my door yesterday.
Doesn't surprise me, moving on.
It's just more homework. I guess that's not a quiz.
Yep, you have a quiz tomorrow.
Oh!
Yay!
Hey, at least I'm here.
Take 2 testaments, but I did got the overview. I don't get to that.
All right.
I'm not so conscious about it.
I'm so conscious for you.
Open up your book. Turn to the first page of section 3.
That 500.
500. Is that what it is?
Yes.
Okay. What we're going to talk about is total internal reflection. Okay? What you get, and you can kind of see at the bottom of this visual here, it shines light at various angles. Okay, you see the visual at the bottom, everybody?
Yes.
Okay, if you shine straight up, it doesn't bend at all. It just goes straight. If you start shining it through or at an angle, it starts to bend. It appears to be bending away from normal. So what does that tell you?
It's going
It's faster. Okay, so it's going from slow to fast, or low or high to low index of refraction. Okay, you could also say when it goes from slow to fast, low density or high density to low density would be another way of looking at that. Okay, eventually it gets to a point where you don't see any refracted light, and all of the light gets reflected. That's known as total internal reflection. Well, I shouldn't say all the light gets reflected, but you don't see the light, the other portion of the light. So here's what I mean. So if light comes straight up, it goes straight through. Here it goes like this. Here it goes like this. And here it would go like this.
They don't show that one.
What angle is that?
in the right on the
You can't see it right there.
Oh, it's just parallel with. They don't
So what would happen is, if it comes in at a certain angle, it wouldn't refract through into the new medium. It would just go straight perpendicular to the normal, or parallel to the surface if you want to look at it like that. And so what ends up happening is like it's reflected instead. Normal is the vertical up to 90. So like 90 degrees to the normal, perpendicular to the normal, or parallel to the surface. You could look at it that way, and probably would be fine. What?
Perpendicular to the surface? Not parallel.
Why would that be parallel?
Why would normal be parallel to the surface?
No, I said the light as it bends would be.
Okay.
Yeah. So what I'm saying is this light would bend so that it would run along the surface, and I'm not 100% sure. I'd have to look this up. I'm not sure if it just won't bend along the surface, and so it all gets reflected. I want to say it's probably that, because it does say total internal reflection. So I'm assuming that it won't, because it would bend at a point where it would go right in between the surfaces. It doesn't even do that, so it all gets reflected. That would be my best guess. I have to look that up for sure.
No, sir.
Why? What do you got to do?
It's not bad.
Okay. So there's a couple of things that need to be true for this to happen. Okay? First off, you've got to be going from a medium where it's moving slow to a medium where it's moving fast. Why?
Because it's fractional, because it's fractional the normal.
It has to be going away from the normal, right? Because if you were going toward the normal, you would never have this. This wouldn't even be a possibility. Does that make sense? Okay? Second thing that needs to be true, the angle needs to be correct. Okay, so the critical angle is whatever, so this would be your normal would be here. Your critical angle would be your angle of incidence that causes it to have total internal reflection, or where it would cause the light to go in between the surfaces. And so instead it reflects. And we can figure out that angle because what's this angle? 90 degrees. So this would be like the incoming angle, the outgoing angle, right? So when we can figure out the critical angle using Snell's law, and I sine of and r sine of 90 is how we would figure out the critical angle. What's sine of 90? 1. So it really, and you'll see on the next slide, it really just removes this. And it's a modified version of Snell's law, so you can figure out what this angle is, which you would call the critical angle instead of the incidence angle, even though they're the same. Well, okay, not the same, but
You said they're the same?
you guys know what I mean when I say they're the same, but they're not the same.
Yeah.
Same. It's the same. It's the angle coming in, but there's only one critical angle. It's the angle where it gives it a 90 degree. It would refract at 90 degrees. Okay. Questions on this? Anything above the critical angle, you're going to get total internal reflection. So I could make this angle bigger and bigger and bigger. Anything above the critical angle, you're still going to have your total internal reflection. Make sense? Yeah, because it would bend so much that it wouldn't even go into the new surface. So anything above your critical angle would never even go into your other medium because of the fact that it would bend so fast that it wouldn't even make it in.
Wait, but
So-
it does at the critical angle as well. So
At the critical angle is where you get that perfect 90,
okay.
and then anything above it would actually be more than that, but it isn't going to even, it's not even going to refract at that point.
Because aren't those angles below it?
I don't mean like below, you're saying it's below here? Is that what you're saying? What do you mean below?
What do you mean above?
Above 90 degrees.
So this angle, let's say the critical angle was 60 degrees. Anything where you had a greater degree than 60 degrees would be above. Does that make sense? Anything below the critical angle of 60 degrees or less than 60 degrees would actually refract.
60 degrees.
Oh.
So you're saying that 60 is the point when it's like.
Well, I just made up a number. I just said I don't know what the actual
Yeah,
critical
you're
angle
saying
is of this problem, but I was saying if the critical angle is 60 degrees, if you came in, if your angle of incidence was less than 60 degrees, it would refract, and if it was 60 degrees or above, it would have total internal refraction.
So how come in this example, the ones that are greater than the 90 degree refract and don't move
Greater
away
than
from
90.
this was 90 angle?
Are you sure? You should dye the tips of your bangs like pink.
Isn't that?
Yeah, I love it.
Alright.
Stop.
This makes the 90 angle, right?
Steve, what is that? What are you guys doing for your haircut?
No, I would, but it's so bad. I don't really need to look at. Wait, like, yeah, put it to the side.
He has to provide for a family.
It's like,
Yeah.
Also, I really don't have time.
So
What?
normal
I
for
have
this point would be
figured it
right
out.
here.
this tool.
Oh, yeah, I got Well, that's what
Yeah,
I'm
you
saying.
getting it, Steve?
Like, the offer right now.
Well, you change it.
I don't know right now.
Zero.
What?
So it looks like
Like-
all the angles have an angle. It can go all the way to here.
I know.
But-
That's where the M goes in that. It's
That is,
So
No, they didn't give us like a cross on the side that crosses on the way though. So that way.
Could you rate that?
Weird certain on the
Mr.
side.
Kramer,
Yeah.
so is the only one that's the total internal reflection is the one that's along the surface?
No, that's when total internal reflection starts.
And then all with.
Every angle greater than that will have total internal reflection. Yes.
Fade is like.
That's
So-
underneath the line.
Shorter.
So it's the angle greater
like-
because
like
it's
it's
shorter
shorter
to
to
wherever it's at.
Until you're bald. And you
Gotcha.
your
So-
first fade,
I like black.
so really long on the sides and back. Make it shorter, 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 shorter.
I was gonna do
Bryce, do a reverse.
So let's say this is the critical angle, and that's 60 degrees. Okay? Here's the normal for that light. Here's the normal for that light. You see how these angles are smaller?
Yes.
Okay? Those will refract. Does that make
Smaller
sense?
than 60.
Yes. So see how those angles are smaller than 60? Okay, but if I get an angle like this, you see how this angle is bigger than the 60?
Yeah, so that'll go.
So that will reflect. So I didn't draw a perfect reflection line, but.
Bigger or smaller based on the normal, not based
Yeah,
on.
based on the normal, yep.
Because I was doing it based on.
Well, that's how we always define incidence angles from the normal. So I was just kind of assuming that.
That's what I said. I said
what I
that.
would think.
That's very great.
Yeah, if you can't see this because it's super gray, write it in or something. This is, so when I said that your critical angle is the angle at which you get that perfect 90 degrees, okay? So there's only one critical angle. However, there's a lot of different angles that could give you a total internal reflection. Does that make sense?
We don't have the part
It's in their
underneath.
light.
It's just, Bryce, it is.
No, I mean, that's not the sine critical angle. The total internal reflection occurs only if you're correct.
The paragraph underneath the equation.
No.
It makes sense.
Kind of
It
important.
makes sense.
Does it make sense, but doesn't make sense?
I mean, it did kind of just make sense. Slow it down.
Yes, so this is important, I guess. Yeah, if it's not in your notes, you might want to make a note. What this is saying is that it has to go from a slow medium to a fast medium. Or another way of saying this would be high N to low N. Does that make sense, everyone? Okay, so then what can happen here is, and this is what this says it here too. The incoming angle has, or incoming index of refraction, it has to be greater than the outgoing index of refraction, which would mean slow to fast. So I showed you, I erased it unfortunately, but I showed you the Snell's law that we use, and you put in sine of 90. What that does is gets rid of that portion of it, so it'd be sine of 90 is 1. I'm going to write it again. Your critical angle is when you've got sine of 90, that will be canceled out. When you solve for, you can just divide by ni here to get your critical angle equation, is where that comes from. Okay? So there's only one critical angle, but that doesn't mean there's only one place where you have total internal reflection. Does that concept make that's important? Because I know that can sometimes get missed in the weeds a little bit as I explain it. So, you ever wonder how mirages happen?
No, I didn't know what it is.
Mirage.
You know what a mirage is?
No.
Really?
Have you not seen
Are we sarcastic? No, I don't know.
Something?
No. Well, I will say that the mirages that they talk about in the movies, that's not real.
Yeah, that's
That's where you like think there's like.
Where you're
places,
hallucinating,
but it's not
basically.
actually.
Oh, you have to be hallucinating. That's probably a better way to say it.
Yeah,
Because
usually what it
in
is-
order to have a mirage, you have to have an object.
I've never heard this term.
So
Yes.
it's actually there, it's just not clear.
Okay, let me explain it. So a mirage is when you've got basically when you see an image and an object. Okay? Now this is important. It says a mirage is produced by the bending of light when it's in different color for a reason. Because what happens is that typically in deserts, or it could happen anywhere, but in deserts is what they usually have context of mirages for. It's because the sun will beat down on the sand, right? The sand will get warm. Well, that'll start to heat up the air molecules right above the sand. Does that make sense? And as you get higher, it cools off and cools off. So what you have is the atmosphere right by the surface of the sand is warmer than the atmosphere above it. Okay? And what happens is light bends more when you've got a high temperature. So, light comes here, it hits the top of this tree, comes down and starts to bend because it's warmer near the surface. It bends, it bends, it bends, it bends, it bends, and then your eye sees it. So basically your eye sees light coming from the same point from two different angles.
So you're telling me that light can stand the sun, but it can't.
The light can stand the sun, but it can't do it.
That makes no sense, Bryce.
The light comes from the sun.
I got you, Bryce.
And then it comes down, and then it's like, oh, the beach is hot, I don't want to touch that.
Oh, gotcha. It's like the sun's real hot.
Is there
The sun produces the light.
Yes, and I mean, I know that the sun is not
And it's moving
actually
away
just
at
light.
an angle that's 90
beach is
degrees
too
from the
hot for the
surface
sun.
of where it came from, so it's not going to bend if it's moving away at 90 degrees.
That cringe.
What if there's a solar flare?
How does it spread back up? Why does it just stay low?
I literally have no idea what the question is.
I don't either.
Okay, the sun produces light. Check, so the light
I mean, I
comes
would
from the
assume
sun,
that
which
it's
is
going
quite
back
warm.
up to
Yes.
the sun.
The sun is quite warm.
So
The sun is quite warm.
Yes.
Quite. So the light comes from
So
the
it's
sun.
bending, bending,
And it
bending,
gets towards
bending.
Earth,
It's
and
still
it's
bending,
like,
but it's bending
oh,
less
the
as it
beach
goes
is hot, I don't
up.
want to touch that.
Because
It's like,
it's going back
so it
from
can come from
high
the sun
temperature to
and be
low
fine,
temperature.
but when it gets to the beach, it's
They're
like, no, that's
moving
hot.
away from where.
Okay, now listen. You see the Mirage every day you drive.
Oh my land. No, on
How
the
many of
road.
you drive and look out in the distance on the road and what does it look like?
That looks like
Oh.
there's water on the ground.
That is a mirage of the sky.
That's the water that high when you drive.
Yeah.
Oh, it looks like it's like, it looks like a hill in the distance.
it's
I
like-
always
When you look, it's easier to see when you're on a highway.
Yeah.
And it's a straight, you're driving on a highway, and you look way out in the distance, it looks like there's water on the road in the distance. And as you get closer, it's like, oh, I'm not hitting this water.
I always call
Well, that's because what it is it's the, because the road is hot, because it's been beat on by the sun, the atmosphere right above the road is warmer than above it, and so light comes in from the sky and bends, hits your eye, and so what you see is an image of the sky on the ground.
No, dude.
I've been wondering for 12 years. My childhood, I did that.
Maybe if it was hot outside, we would.
I would always tell my so like when I look farther at the road, I'll see clouds. Is that
No,
what
you'll see water.
I'll see
Well,
water.
it looks like water.
It's not water, but it's really the clouds.
Okay.
Alright,
Clouds
like
are
more this summer when I'm driving on the interstate.
So cool.
Alright, this version, you probably already know this. Now, everything that we've done up to this point when we've talked about refraction has been, we've been assuming we're dealing with one wavelength because every wavelength of light refracts a little bit differently. Okay? This is why when you put a prism up with white light coming in through a prism, this is why you see what through a prism?
Multiple colors.
The rainbow is because white light's coming through the prism and all the wavelengths of your visible spectrum are separating and then you see the different colors as a result.
Sir.
Okay? That's dispersion. Okay? I wonder, I don't know for sure, this is a theory, I wonder if when the sun goes below the horizon,
Oh, that's tragic.
and you can't see the sun anymore, but you can see the light because we know it bends through the atmosphere. You're going from a vacuum, essentially in outer space, to air. I wonder if that's why you see the various colors
Of a sunset.
of a sunset. Is because light, the different wavelengths refract at a different amount. That would be my guess. But
You can't say that.
I thought it was just, yeah, it's like
So then you would-
water not allowed.
it might be some of that too. Again, the only reason why I say that's a theory is because wouldn't you see that every night then?
I just go try.
So
Sometimes it's.
it probably has a part to do with it, but not probably the only reason.
Oh, I watched a video about that. I just didn't know it right now. It's like, yeah, like, I forgot what the reason was, but like, the red wavelength's longer, so you see it more.
Yeah, I mean the red wavelength is going to bend less
We saw like the toxic.
All right, this is I don't know. I think this is really cool.
This is a lot better than our.
Yeah.
The rainbow.
You guys are funny.
This is a physical reality.
So there are two things that have to happen for you to see a rainbow.
She's so close to it.
One, the sun has to be behind you,
It's a black lady.
and two, you have to have water molecules in the air.
Is that where you know it is, Cole?
Okay? So technically, if the sun is in front of you and it's raining in front of you, you will never see a rainbow.
Oh my lands.
Here's how it works.
So wait. So like a rainbow isn't always the same place for everyone.
I don't
It
know.
would be awkward to be like,
I don't see it.
Now
You could
listen.
never reach the pot of gold.
Never. Right.
Science is ruining
Or everyone will reach the pot of gold, just at different locations.
Wow.
Alright, now listen, let me finish. The reason why it has to be in behind you is because light rays from the sun will come behind, they'll hit the water molecule that's in the air. So, because the water molecule is a different medium, it will bend the light. Okay? Creating the different wavelengths so you can see the different colors of light. Well, then it reflects due to total internal reflection and will bend back and refract again so that it comes back to your eyes.
So then.
So is this happening? Is this happening if you could see sun? You won't see the rainbow, but somebody on the other side could see the rainbow. Like if they were facing the other direction.
So then, like, can you just turn around and see the rainbow?
No, because then the water's not there.
Try it
If
again.
it's raining everywhere around you, and you turn around,
There's a rain. You just keep turning the rainbow. This is how
There's sun there. If I look this way, I'll see a rainbow.
So then,
why would that
so
work?
live
There's
is like,
270
is it just the amount of light refracted that depends like how big the rainbow is?
Yeah, so it has to be the right, you have to have the right sun location as well.
Why is it?
Why is it-
Could you have a cloud?
Why is it
This
arch?
whole thing is.
Yeah, why is it arch?
Why is it just so much space?
My guess, this is theory, my guess is because of the spherical shape of a water droplet. And so when it hits, like this looks like just two dimensions, right? But it's going to be light coming off various different
Like a
curvatures
dome.
of the water droplet. So
Wait, if
that would be my guess.
also, cool, if that's the case, is it, what's a double rainbow?
Yeah.
Is that when the light is like refracted off of the
Explain to me what a double rainbow is.
So it's like, there's just two arches.
Yeah, like you can see a rainbow, but then there's like another one.
There's
Another
another
arch.
arch. That's like a triple rainbow.
A rainbow actually comes off spherical.
Because they say that it's a lot of, like, a lot of people say the rainbow, the light is then refracted off the light of the first rainbow.
It's possible. It probably is a double length, like
Yeah.
similar to having two water droplets in the right spot.
They say it's impossible for a triple rainbow because it can't like reflect off of itself.
No,
and
he
then
was just
reflect off of it.
That makes sense. Hey, let's do a critical angle problem. So we said sine of our critical angle was, I can't remember, NR over NI or NI over NR?
That's all one of
Okay? Find the critical angle for water-air boundary if the index of refraction of water, I'm saying water to air. Okay, what does it have to be in order for it? Is it water going into air or going into water?
What in the water?
It's gotta be water.
It cannot be both. Remember, there are some specific guidelines for
Water to air.
has to go from water to air. Why?
Higher index of refraction to lower.
It has to go from slow to fast. Right?
Oh,
Has to go from slow to fast.
Because it goes from fast to slow to fast. Oh, that's true.
Water's slower than air.
It goes from. Oh no, never mind. It's on. Because it goes from air to water.
When it goes in here, it goes from air to water, but then it won't go from water back to air because of total internal reflection. Does that make sense?
Wait, but then afterwards, then
Do you want me to slow down and explain that a little bit more? It bends here, but won't here because of the total internal, because it'll be going from slow to fast to get out here.
Oh my word.
So you need to go from fast to slow.
No, the opposite.
It's slow to fast. So why can't you go from water to air?
Because it'd be going from slow, wait, no, that's what we said, going from water to air. That's what it is.
Oh, okay.
Yes.
Isn't it when it comes back out the other side, going water to air though? Like when it goes in and then total internal refraction or whatever, and then comes back out, that would be water to air.
No, that's, when it comes
So I'm
out.
saying
that's
this
reflection,
is
that's
water,
refraction.
this is air. So what do you, so then we'll never get to the air.
When you showed the water drop.
Yeah, with the water.
Oh, okay, that's what I was trying to explain to Lauren.
Yeah.
Comes in here, goes from air to water, so that slows it down, right? But then now we're H2O here, and we're air over here. So when it comes in here, it's going from slow to fast, which it can have in total internal reflection when you go from slow to fast. That's why it reflects there.
And it never comes out the other side.
I'm guessing it has to be the angle. Yeah. It has to be the angle that when it hits the back, it will reflect, but when it comes out, the angle is not the critical angle, so it will reflect. Yeah. It has to be the angle. I don't know, but I don't know exactly, but it had to be a lower angle. Otherwise, you're right. You're right. It would continue to bounce around if it was like that. Yeah.
And then you would never see it.
Yeah. Which it's possible that. So it's possible the sun has to be at a specific point in relation to you.
That's why you don't always see it.
Yeah, like you don't always see a rainbow if you've got sun behind you and water in front of you.
Grams, I always see a rainbow line.
Yeah.
Issue.
Okay, so in this one, we know that our starting index is going to be the water, so 1.33 over 1.
No, we didn't.
Oh,
No.
my God.
That makes sense?
This is starting water.
I thought it was, wait, is NI or NR 1.33?
R over NI. The incoming will always be slower, which means higher index of
The
refraction.
bottom will always be one.
Yes.
It'll always be.
And top will always be one. No. Wait,
Yeah.
which one is okay, sorry. Which one is NR? Which one is NI?
NI is your incidence coming in, and R is your refracted, okay? And we know it has to go from slow to fast, which means it has to go from high to low. High to low.
Is that always, all these problems will be
For the critical angle.
low over high?
Yeah, you always have a bigger number for critical angle problems on bottom. You always have a bigger number on bottom when you're doing critical angle problems. So then you have to do, then you have to do inverse sign.
So is that the only way that you know that that one's on bottom? That's the context of the problem.
So the context of the problem, you'd have to know that in order for it to have total internal reflection or a critical angle, you have to go from slow to fast or high to
That's the
low.
only way you can know.
In this context, yes.
But other ones will probably.
Kramer.
When you do that, you should get 48.8%. Let me find out what.
Because it says water air, is that water?
That's so gross. He does that.
I was telling him, it doesn't really make it very clear in the context of which it's coming from, which one it's going to. You would have to understand, you would have to know that it has to go from slow to fast.
Yes!
High index to a low index.
Yes!
So which means you have to put the water on bottom because that's the higher index. Yeah, I'd like you to be able to conceptualize that. Yeah, it is. Oh, yeah.
Emma, hurry.
Yes! But we do so much review in class.
Give me your stuff. Atta girl.
I don't know. No, you're right.
Hoping that was my
Understand why I was thinking. Yeah. I believe you, and I'm sorry. I just got
All right, have a seat. We got a short day, our short class, so let's get going on this test.
Yeah, this is gonna be fun.
I love celebrating learning.
I know.
Don't
It probably will.
Kramer,
Wait,
put it
wait,
here.
no, I don't have to make that.
Whoa, that's cool. You said how'd you do that?
It's just a normal crane.
That's not normal.
Okay, I need to see.
This match.
Oh, you're right, Rose. Oh.
Hey, do you have the momentum equation? Or momentum equation worksheet done? And Audrey and Shane, yours, I just haven't put it. Everyone should be good, so I don't give any zeros. Woohoo! Woohoo!
Where's that?
Whoa.
That I did like this. Kramer.
I need a shoe.
So where?
He
So
gave us some cheese.
this be the sentence here or what?
Yeah, so definition.
That much? Sentence, picture? That's why.
Kramer.
What?
We went undefeated last night.
I think I found another one.
We did?
It's okay.
I didn't even know. I was basically going half speed, so.
Normal force.
And you're like, yeah, don't let Steve.
Let's get up to
At that point, I give it.
Yeah, we should hide that.
Oh, all right, no cards.
So was I, so I'm always going to.
Well, I forgot my thing on that, I have you send it to me, and then I
Like
got
net
that
force,
force,
but it's like looking for inertia.
All right, anybody else have the cards that are noted?
Nice, like,
Damn, those aren't no cards.
so if one's going this way, one's going that way, and it's zero,
They are.
and it's completely balanced, but like,
You're kidding,
it's like one or something, one has a little bit more force than the other. So if there's no net force, there's no telling.
Oh, okay.
You can know it's
Gravity, gravitational attraction.
Oh,
Johnny, when are you gonna get your phone back?
I have it back.
You do? Okay.
Anybody else?
Tomorrow about your chips.
Oh, I got them. This man came and helped.
This does seem a lot easier.
I'm
You
actually.
haven't even seen the test. How do you know?
There's no way I'm finishing this. I
All right, put it anyway. What?
I feel good about this test, but we can get this.
Hey, I asked you to put stuff away. Still see some of you not doing it.
Come on, guys.
I felt good about this test like 3 minutes ago. I have, and now,
Yeah.
So what?
it's closed.
I remember what
The only way.
that sounds like a lot of work.
Yeah, too much.
I feel like nobody's bitching about
The water
it.
bottle.
It's almost
Takes it back.
All right.
Good, 5 minutes. 5
Do I
minutes.
get this row to move out?
You do what? You
Maybe
pick it out.
just go over more.
Hot. You're new. Did he pack? I would probably do something like that and break it on
You guys move just a little bit that way, not much. My dad's probably. You guys move just a little bit this way. Yeah. Good. Perfect.
It's chilly today.
Oh, I love it.
Oh, it's chilly?
Nervous.
Before a big game.
Yeah, it's kind of like that.
What? I always knew when I was gonna play well and when I wasn't,
How?
based on how much nerves I had before.
I mean, like, if you're really nervous, did you know you're gonna play well?
Like good, man.
Oh, really?
Yeah, because I was hyped, I was ready to go.
So make yourself nervous.
Alright, that was just me. That's not the case for everybody.
Oh, my calculator's in my box.
This is really interesting.
Hey, I gave you the test. It shouldn't be talking anymore. Your equations are on the board.